What if I told you that a single dam can produce enough clean electricity to power around 100 million people? It sounds like something from a science fiction movie, but China is taking hydropower to a completely new level. Today, giant dams are no longer just walls holding back rivers. They are becoming intelligent power stations, using artificial intelligence to monitor equipment, predict failures before they happen, and deliver electricity exactly where it is needed. This is the story of how smart engineering and AI are changing one of the world's oldest sources of renewable energy. For thousands of years, humans have relied on rivers. They provided drinking water, transportation, irrigation, and food. But in the last century, engineers discovered that rivers could provide something even more valuable: electricity. Hydropower quickly became one of the most reliable sources of renewable energy. Unlike solar panels, which only generate electricity during the day, or wind turbines, which depend on the weather, a river can produce power 24 hours a day as long as water continues flowing. China understood this opportunity better than almost any other nation. Over the past few decades, the country's economy has expanded at an incredible pace. New factories, high-speed railways, electric vehicles, and growing cities all have one thing in common: they require enormous amounts of electricity. Supplying that energy using only coal would increase pollution and carbon emissions. Depending entirely on solar and wind would also create challenges because those sources are naturally unpredictable. So China invested heavily in hydropower. Today, the country operates more hydroelectric stations than any other nation on Earth. Some of them are so massive that they can be seen from space. Among these engineering giants stands the Three Gorges Dam, still the world's largest hydroelectric power station by installed generating capacity. It can produce more than 22 gigawatts of electricity, enough to supply tens of millions of homes under favorable conditions. But building a giant dam is only the beginning. Keeping such a massive system running safely every second of every day is a completely different challenge. Imagine managing thousands of sensors, dozens of giant turbines, hundreds of gates, and millions of liters of water flowing every single second. Even a small problem inside one turbine could reduce power production or damage expensive equipment. Traditional inspections rely heavily on scheduled maintenance. Engineers stop machines, inspect them, repair worn parts, and restart operations. While this approach works, it isn't always efficient. Sometimes equipment is serviced before it actually needs maintenance. Other times, hidden problems remain unnoticed until they become serious failures. This is where artificial intelligence begins to transform the picture. Instead of waiting for something to go wrong, AI systems continuously analyze data collected from thousands of sensors placed throughout the dam. These sensors measure vibration, temperature, pressure, water flow, electrical output, and countless other parameters every second. To a human engineer, reviewing all this information manually would be almost impossible. But AI systems are designed to recognize patterns hidden inside enormous amounts of data. If a turbine begins vibrating slightly more than normal, AI may notice it long before engineers can detect the change. If a bearing starts heating unusually, the system can immediately flag the issue. If water pressure changes unexpectedly, operators receive instant warnings. Instead of reacting to failures, engineers can prevent them before they happen. This approach is known as predictive maintenance. Rather than replacing parts according to a fixed schedule, maintenance teams repair equipment only when data shows it is actually needed. The result is lower maintenance costs, fewer unexpected shutdowns, and greater reliability. But monitoring machines is only one part of the story. The real challenge comes from managing the river itself. Every second, enormous volumes of water arrive at the dam. During heavy rainfall, water levels can rise dramatically. During dry seasons, water becomes much more limited. Operators must constantly decide how much water should generate electricity, how much should be stored, and how much should be released downstream. Making the wrong decision could reduce electricity production or increase flood risks. Traditionally, these decisions depended largely on human experience supported by weather forecasts. Today, advanced computer models and AI-assisted forecasting are making those decisions smarter than ever before. By analyzing weather data, rainfall predictions, upstream river conditions, and historical patterns, AI systems can help operators estimate how much water is likely to arrive over the coming hours or even days. This allows dam operators to prepare in advance instead of reacting after conditions change. And that's only the beginning, because generating electricity is actually the easier part. The much bigger engineering challenge begins after the electricity leaves the dam. How do you deliver enormous amounts of clean power across thousands of kilometers without wasting it? That question changed the future of China's energy system, and the answer lies in one of the world's most advanced power transmission networks. Generating electricity inside a giant dam is only half the challenge. The real test begins the moment that electricity leaves the turbines. Imagine producing enough electricity to power an entire country, but having no efficient way to deliver it where people actually need it. Much of China's clean energy is generated far from its biggest cities. Massive hydroelectric stations are often located deep in mountainous regions where powerful rivers flow naturally. Meanwhile, China's largest industrial centers are hundreds or even thousands of kilometers away. Factories in Shanghai, technology companies in Shenzhen, manufacturing hubs around Guangzhou, and millions of homes across eastern China all need electricity every second of the day. Transporting that energy over such enormous distances isn't as simple as running a few power lines. Every kilometer creates resistance, and resistance means energy loss. Think of it like water flowing through a long pipe. The farther it travels, the more pressure is lost. Electricity behaves in a similar way. If engineers used ordinary transmission lines for these enormous distances, a significant amount of electricity would simply disappear as heat before reaching its destination. China's answer was to build one of the world's largest ultra-high voltage, or UHV, power networks. These transmission lines operate at voltages far higher than conventional power grids. Why? Because increasing voltage allows electricity to travel much longer distances while reducing energy losses. Some of these lines stretch for more than 2,000 kilometers, carrying clean electricity from western hydropower stations to eastern megacities. From the air, they look like endless steel highways crossing mountains, deserts, forests, and rivers. Together, they form a nationwide electrical backbone connecting different regions into one enormous intelligent network. But transmitting electricity is only part of the story. Demand for electricity changes constantly. Every morning, millions of people wake up. Lights turn on. Coffee machines start brewing. Factories begin operating. Subways fill with passengers. Electricity demand rises sharply. Later in the evening, families return home. Air conditioners switch on. Televisions begin streaming. Electric vehicle owners plug in their cars. Demand rises again. Meanwhile, late at night, much of the country goes to sleep. Demand falls dramatically. The power grid must constantly balance these changes. If too little electricity is available, blackouts can occur. If too much electricity is produced, valuable energy may be wasted. Finding that perfect balance every second is incredibly complicated. Years ago, this depended almost entirely on experienced grid operators making decisions based on forecasts and historical data. Today, artificial intelligence is becoming an important decision support tool. Modern grid management systems analyze millions of data points every second. Weather forecasts, electricity demand, river flow, wind speed, solar generation, industrial consumption, even seasonal patterns. Using all this information, AI-assisted systems can help operators predict future demand with remarkable accuracy. Imagine that weather forecasts predict unusually high temperatures tomorrow afternoon. Millions of air conditioners will likely switch on. The system recognizes this hours in advance. Operators can increase electricity generation from hydropower stations before demand reaches its peak. Now imagine another situation. Strong winds suddenly increase electricity production from nearby wind farms. Instead of wasting that extra renewable energy, operators may reduce hydropower generation temporarily, conserving water inside reservoirs for later use. When the wind slows down again, hydropower can quickly increase production. This flexibility is one of hydropower's greatest strengths. Unlike coal-fired power plants, which often require hours to change output, hydroelectric turbines can respond much more rapidly. Some turbines can increase or decrease power within just a few minutes. That makes them ideal partners for renewable energy sources like wind and solar. As more renewable electricity enters the grid, balancing supply and demand becomes increasingly difficult. Artificial intelligence helps operators manage this complexity, not by replacing human engineers, but by giving them better information and faster analysis. Another remarkable technology supporting modern dams is something called a digital twin. At first, the name sounds futuristic, but the idea is surprisingly simple. A digital twin is a highly detailed virtual copy of a real structure. Engineers create a computer model of the entire dam, including turbines, generators, spillways, transformers, and other critical equipment. Thousands of sensors continuously send real-world information into this digital model. The virtual dam updates almost instantly. If a turbine begins vibrating slightly more than normal, the digital twin reflects that change. If water pressure increases, engineers can see it immediately. Instead of waiting for equipment to fail, they can simulate different maintenance strategies inside the virtual model before touching the real machine. It's like having a complete practice version of the dam that allows engineers to test ideas without any risk. This technology is already being adopted in many industries, from aviation to manufacturing, and it is increasingly finding applications in large infrastructure projects. Of course, none of these technologies eliminate the need for experienced engineers. Artificial intelligence doesn't replace decades of engineering knowledge. It enhances it. Human operators still make the final decisions. They interpret recommendations. They consider environmental conditions. They evaluate safety. AI simply helps them process information much faster than any person could alone. This partnership between human expertise and intelligent software is becoming one of the defining features of modern infrastructure. Yet electricity generation isn't the only responsibility of a mega dam. In many ways, its most important job has nothing to do with power at all. Because when millions of people live downstream, controlling water can become just as important as generating electricity. And that's where these engineering giants face one of their greatest challenges. Every drop of water must be managed with extraordinary precision. In the next part, we'll explore how modern mega dams help control floods, protect cities, support navigation, and how AI-assisted forecasting is making these massive structures safer and more efficient than ever before.